Chapter 18. We're going to talk about a few problems today that we worked in class. We're going to start with number 15. Now, it's asking you what's the mean and standard deviation for a situation like this. First of all, the word mean is a bit misleading. This is a categorical question, right? So really we're asking what's the center of the scenario? Well, they tell you the problem that the 7% of the people make late payments. So your center is going to be 7% for all of your samples too. No calculation needed. Standard deviation, I'm going to pull up the categorical formula, the standard deviation of p hat, that's p times q over n, and take the square root of that. That's going to give me my new standard deviation. I know it's categorical. Number one, they use the word proportion, or I just think about the question. It's a yes or no question, so clearly categorical. The next part, we're going to kind of check on our assumptions and conditions. Now, a little bit about this. When you do something like this, you can't make a list of the assumptions or the conditions and just kind of check them off. It doesn't work like that. You're going to have to write out why it's satisfied or why it's not. And that can be a short phrase or it can be a full-on sentence, right? I'm not requiring either of those, but just make sure that you do it completely, right? So the first thing, when we talk about a random sample, note that when you read that question, chapter 18, number 15, it doesn't say anything about a random sample. So really what we're talking about here is I want to make sure that the sample itself is at least not biased. It's a representative sample, that every other sample taken from that population would also be just about the same. In this case, we're going to say it's not random, but it's a representative sample. For independence / 10%, whenever you're sampling without replacement, you are not going to use independence, right? Because it's not independent. We're going to be using 10%. We know that if we chose 200, that's going to be less than 10% of all people who would have gotten a loan in this situation. We know that because there would be thousands of people, possibly millions of people that would have been in possible banks that could have gotten a loan in this kind of situation. So I don't have to really worry about that kind of sample size. There's more than 2,000 people getting a loan. Okay. The next part is the easiest one. We have success and failure, the condition. What that says is I need to know if it's okay for me to use the normal model in this case. We do that by doing n times p and n times q, and that allows us to know if the sample size is large enough for me to use a normal model. And here it definitely is 14 and 186. Both are greater than or equal to 10. And so I definitely have the ability to use the normal model. And that's what it's going to ask me to do next. In this part of the question, it's asking me to consider what's the probability that if I had a scenario like this, that 10% of this particular situation, what's probably that more than 10% of the people would have been late on their payments or not make timely payments as it says. And so the first thing I want to do is I want to draw this picture. The important part here is I'm going to demonstrate to my grader, to my reader, that I understand all of the different elements. I show you here that I have a mean, a center of 7%. I have a boundary of at 10% and greater. I could write this out in words or I can just simply draw this picture. It defines every single one of these except for this. All right, and we did that earlier up in the problem, so that was defined already. We get down to 4.8% or 0.048 as a probability. You're not done. In this chapter, it is crucial that you understand the problem, that you know how to explain what those numbers mean. So you're going to have to practice much more later to come, but now we're going to get practice at it, writing my conclusions in context of the problem. So I need you to understand what this 4.8% or the 0.048 as a proportion or probability means. Right? Go back to the question. It's asking what's the chance that more than 10% of the people would be late on their payments, right? Well, there's a 4.8% chance that more than 10% of the clients will not make timely payments. If you go back and read your question, usually it gives you a really good way to write out your conclusion. Yes, this seems a little tedious. And that's the way it is, right? Get used to it, get practice doing it, writing it out so that it sounds nice and smooth and not too awkward. But pay attention to those kinds of things. Number 17, this is asking us a question about number of students who go back. As freshmen, they go to a school, and then as a sophomore, they go back to the same school. The school retains them. And so there's a 74% of the freshmen that they surveyed from the ACT said they're going to go back to their school that they went to as freshmen, as sophomores. So it's really just setting it up. It's asking me to check my assumptions, my conditions, and to kind of write out the 68, 95, 99.7 scenario. First thing I have to do, I need to make sure that it's normal before I even do a 68, 95, 99.7 rule. So we're going to run through it here, right? So randomness, it actually told us it was random. So you can simply say the word stated in the problem, stated as random samples, however you want to say it. Here again, we're sampling without replacement, so really we're not doing independence, we're doing the 10%. So we're doing 400 times 10, this is going to be 4,000. Are there 4,000 freshmen in college that would go back as sophomores? Absolutely, without a doubt, that's true. So I definitely have less than 10% of my population. Last part we're going to do is success and failure. We're going to check N times P, which is 400 times 0.74 to get 296. And the same thing again, we're going to do the same thing, 400 times 0.26, the inverse or the complement of 0.74. Both of these are definitely much larger than 10, so a normal model is totally possible here. One thing that when you write out this kind of thing, you're saying that a normal model works. Usually you want to know the mean, or in this case the proportion, as well as the standard deviation that you're going to be working with. Okay, so because everything has been met, you would work it out. Now, when would it fail? If you do not have a random sample, that's a major problem. If success or failure doesn't meet, I really would probably have more of a skewed distribution, and I would say it's not appropriate to use a normal model to use in this situation. Remember that p hat, the center for p hat is going to be the same as the population, so it's going to be 0.74. And we're going to kind of run back into that categorical formula for the standard deviation of the problem. So it's p times q divided by n. We're going to get 0.022. You are also welcome to write these things as proportions or probabilities, right? This could be 74%. This could be 2.2%. That brings up a really important issue. Here I could say 74%. I could say 0.74. I could use a percent or a proportion. I could even do 296 people. So I'm running into multiple ways to write out my solutions, and all of them can definitely be correct. But you need to pick a way, and you need to make all of your values go with it. I'm going to suggest this one. I'm going to suggest keeping it as a decimal, as a proportion. Because your calculation for standard deviation, one of the probably the most common calculations, is always going to be as a proportion first. Now, if you don't like that and you're pretty comfortable doing it that way, that's totally fine. Instead of putting 74% or 0.74 here, I could have written 296, and I could have added, right? You can multiply 400 times the standard deviation and get this to be in terms of people instead of just proportions. And I can work out that situation both ways. Be careful. That is a major downfall for a lot of students in this chapter. They don't really work out in their own head how to keep everything in the same unit, and that really causes lots of problems on the test. Okay, make sure that's an issue you know about and you keep doing it. One of the big clues is when you do normal CDF. This question didn't ask that, but if I do normal CDF, I get 0 or 1. That's not always the case, but sometimes if I ever get 0 or 1 in a probability when in a situation I'm working like this, I'm going to double check my numbers, make sure I did it right. Right? And I'll show you in a minute another one where you do get 0, and I got a way to check to make sure that makes sense. Okay, so here you go. In this case, you had 68% falling between these two numbers at the bottom, 95 between these two numbers, and 99.7 falling between these two. This is sufficient for representing your 68, 95, 99.7 rule. You worked it out that way. Question 19 is a continuation from question 17. They wanted to know if you had a college that had 522 out of 603 freshmen come back, then do they have bragging rights? Well, the first thing I want to know is, well, what percentage is that? I know that the national percentage, they tell us is 74% from the paragraph or from the problem above in 17. We can find p hat by doing x over n. That's the number of successes divided by the total sample size. That gives us 86.6%, or a proportion of 0.866. I don't need to check my assumptions again because we did that in number 17. The only difference here is that we have a larger sample size, which means if it was normal before with only 400, I'm definitely going to have an even more normal scenario with a larger sample size. So we're good to go on that part. Drawing my picture out here, kind of saying that I'd like to know what's the likelihood I could get a probability, or that I could get a percentage of 86.86 if the real percentage of this is going to be 74%. So we'd like to know what's the chance that, assuming that the true percentage is 74, that we could just randomly get one that's as high as 86.6% or 0.866. Okay, it's a normal CDF question. I need to make sure that, and I really, really encourage you to think about this, because anytime sample size changes, I have to redo standard deviation every single time. And that happens multiple times, especially when you're dealing with different sample sizes. All right, and I can plug this all into normal CDF, and we can get and it's interesting, you should do this. If you haven't done it before, don't take my word for it, but do it, and you're going to get scientific notation here. It's going to be that, but it's not going to show you that. It's going to be, I think it's like 1.2 something times, well, e to the negative 12. And the way we deal with that, if you've never really dealt with scientific notation before, the decimal stops or happens here. I'm going to go 12 spaces to the left, right? And that's what that number shows up to be. That's essentially 0, right? I don't need you to write this ever. You can just say this is approximately 0, right? Usually once you go past 4 or 5 decimal places and it's all zeros, I'm going to pretty much say that that's essentially approximately 0. In this case, that means they have the right to brag. Now, we need to pause for a minute. And this 0% is the correct number, but do you know what that means? Do you know how to interpret that? It's essentially like this. What is the chance that a school would have this many freshmen come back out of a total number of 603 freshmen to come back to school in their sophomore year if the true percentage is only 74%? Could we just randomly one year get a fairly high number and it be this high just by random chance? And the answer is no. There's about a 0% chance that you could get some number this high if the real percentage is all the way down here at 74. Now, I'll be honest, a lot of the times if I do normal CDF and I get 0, my first thought is I just typed something in wrong, okay? But I told you earlier there's another way to check that. Here we go. When I have a value, I want to kind of check to see if it's really, really far away and really unusual. I'm going to put it into the z-score, okay? This is a new z-score formula, or new version of it. It's p hat minus p divided by the square root of pq over n. Now, let's be clear. That's statistic minus parameter divided by standard deviation. That is how the z-score formula has always worked from the very beginning, right? That's why on your formula sheet you don't see a z-score formula, not like you see here. It's written out in those words because there are a ton of different versions of this. In fact, almost every chapter from here to the end of the semester, we're going to get a different or slightly different version of this formula. Keep that in mind. Anyway, it's 7 standard deviations away. We know that if it's 2 or 3, we can call that unusual. So this is not just 2 or 3 or even 4. This is so far away that it doesn't even really make sense. That's why it's that small, 0, right? So that's just really crazy far away, which makes perfect sense that I get a probability of 0. So yes, they do have bragging rights. There's almost no chance that they could have a rate this high when the real percentage is down here. So we really think, well, my math is pretty sound. I checked my assumptions. This seems to be pretty good. So my assumption that I started with, that's probably what's false. Number 23. Here we have a batch of apples are selected from a major population, and we get a sample of 150. They tell us that we have a random sample was taken and that the real percent of bad apples in this group is about 8%, right? We see that number right here. However, they tell us that if a batch is 5% or less, then we'll consider that acceptable and we'll ship that off. If that is actually more than that, then we're going to say, no, it's bad. We need to kind of pull those back in and redo them, pull out some bad ones, and refix and redo the batch. So here, what we're looking at is we are trying to show all of my assumptions and conditions are set up so that I can show that normal CDF is appropriate. So we have random. Yeah, it's random. They tell us in the problem it's random. So I can just simply say it was stated. It was in the problem. 10% here, 150 is definitely less than 10% of all the apples that would be considered. 150 times 10 is 1,500. So you know there's more than 1,500 apples in a given farm or whatever. Success or failure would be just like this, the 0.08 times 150, and then 0.92 times 150. Here again, that's close, but it's still inside that range. It's okay. We have 12 and 138. Because both of these are greater than or equal to 10, we can say that all of my assumptions are good and a normal model will be appropriate. The center of this distribution is going to be at 8% or 0.08. And I'm going to calculate my standard deviation by using that formula. Here again, this is a proportion. We're using P, and it makes it categorical. 0.08 times 0.92 divided by 150. I'll take the square root of the whole thing. That's going to be 0.022. I want to know what is the probability that this batch gets accepted even though it should be rejected. So I really want to know what's the chance that I could take a sample from this group and it actually be in that less than 5% range, right? In the acceptable range. And so here I'm going to draw the curve out, label it like I need to. Part of this comes from just understanding what the question's saying. And here again, we'll say, well, that's from negative infinity down here all the way up to 5%. And then the center is at 0.08, and of course we found the standard deviation to be 0.022, right? When I work that out, I'm going to get about 0.0, I think at 0.863 is the correct answer. And that's it, right? So you'd say about 8.6% of the time, a batch like this would get passed on as acceptable batch of apples. Somehow I'm not sure where this text went. This used to be here, and I must have erased it. But essentially what I just said, we would be about 8.6% confident, about 8.6% of the time, this batch would get accepted or would be considered unsatisfactory, whatever the question was saying. They would accept it about 8.6% of the time, when in fact it really is unsatisfactory. Number 41. I don't believe this one was on your list of questions, but I think it's a good question to go over. This goes back to chapters, I believe, 16 and even into 17 just a little bit. This one is asking us to look at a probability distribution table, right? So I can tell you here that X's in this case are the amount of money won. If I get an odd number, it's $0. I'm going to get that 1/2 of the time. 2 or 4, I'm going to get a $1 award. That happens 1/3 of the time. And then if I get a 6, I'm going to get a $10 prize. That's going to happen 1/6 of the time. If you remember, we did the expected value where we did the probability, the outcome times the probability, and we added it all together. And you can do that easily just with the calculator, or I can do it in my lists. Remember that X gets L1, my P of X is L2, and then I'm going to use my one variable stats to do the whole thing. That's going to get me E of X, that's the X bar result, and then your sigma, the O with a little tail on it, is going to be your 3.6, or it might even be 3.61. And that's how you get the mean and the standard deviation. Now remember, part B says I want to do this 2 times. So that's like doing X plus X. Do you remember when we added things together? We combined different distributions, right? Well, 2 plus 2 is 4. That's easy. Remember, standard deviation doesn't add. Only the variances add. So we take our original 3.6, we square it, we add it up, and then we square root that value, you're going to get 5.09. If you went with 3.61, I think you get 5.10. So essentially the same numbers. Part C is where it gets a little bit tricky. It's saying, okay, so well, what if we did it 40 times? Well, I'm not working all the numbers that I have. And it's asking for a probability here. It's not asking what would you expect to win after 40 tries. right? Obviously, that would be like $80, right? But I want to do, here, I'm mixing units. I don't want to mix units with 40 times and units with 1 time. So what I'm really going to do is I'm going to take the prize I won divided by the number of tries. That would say, on average, for the individual try, I'm going to get $2.50 per game. What is the probability that I can average $2.50 each time? If I can figure that out, that's going to tell me the probability that I could get 100 on average after 40 tries. Well, let's check our assumptions to make sure that this follows normal model. First of all, it's random because I'm rolling a die. It's also totally independent because it's dice, right? If I roll a die, it's by definition random and independent, so I don't have to worry about all of that stuff. The central limit theorem, which is what we've been discussing most of today, basically says this will follow a normal model. Okay, infinite sample sizes, by the way, like rolling a die, flipping a coin, I don't need to do a 10% thing because it truly is independent. So 10% for this scenario doesn't even matter, right? Rolling a die is actually normal. It is a normal scenario when you add up the different values. I'm going to take a sample size that's large enough here. 100 obviously is large enough, and I can figure that out. We can go from there. But let's go back in here. I'm going to take a center of 2. That's $2 on average. And I'm going to be taking a probability that's greater than 2.5. So we have to recalculate standard deviation. We had originally 3.6. But now we're going to be averaging the results together. Anytime I take an average result, I'm using a sampling distribution. And by the central limit theorem, that's what this part says, that guarantees me normality because we're doing averages now, not the individual results. So by using normal CDF, we can go through all of this, and it's about 19%. You say, according to this model, and we're definitely not exact, right? Every time you do this, you're going to get the same thing. So we can estimate this value. And I'm going to say that this is an approximation. I don't want to give out the idea that I'm going to win exactly $100 every single time I try this, if this happens, right? It may be, the probability is roughly 19% here. So don't give out like I'm proving something. You are not proving anything.